Welcome everyone to my channel. We are moving towards the conclusion of our video lecture series based on vector analysis. We are discussing all the topics and all the derivations, the figures you need to draw, the definitions you need to write, and how you need to perform the complete derivation on the topic. Now, today we are going to discuss conservative field. As I promised that after line integral of vector field, we shall discuss conservative field. But in between, we did two rules which state that divergence of curl is always 0 and curl of gradient is also always 0. So now let's start with conservative field. You must have read about conservative field in your early physics courses. Well, the meaning is the same. It means that this field depends only on the initial and final points and not on the path taken. As you can see here, these are the 2 points A and B, and no matter whatever sort of path you draw, see, we can draw a straight line also between them, we can draw a curve, and even we can draw any sort of path between these 2 points. But a conservative field, well, of course it can be a vector field. Its value will only depend on A and B and not on the path taken. So no matter whichever path you take to go from A to B, the values of the vector function will stay the same. Similarly, here as you can see, we have this point A and point B, and there are like 3 different paths being drawn between these 2 points. So if the field, and you can see all these arrows, they denote that some field is present. So A and B are the 2 points within that field. So everywhere you can see these red arrows are present. So field is present in this complete region. Now if it's a conservative field, that means that its value will simply depend on the initial and final point, and it will not depend on the path taken. No matter whatever path you draw between these 2 points, the answer will simply depend on the limits, because after all it's a field and we know that we have to take line integral because these are basically curves or the lines drawn. So we have to take the line integral. So if we have to integrate it, in that case we have to put the limits. So the answer would solely depend on the limits and not on anything else. As we have done in line integral of a vector field, suppose we have a vector A, which obviously depends on x, y and z. Then if we have to mention the line integral of this vector field A from A to B along path C is defined like this. We already know that we have to take dot product between vector field A and this change in position vector represented by dr, and this dr includes the changes in all the 3 coordinates. Okay, so this is the way, and since 2 points are involved A and B, so we have to integrate it from point A to B, and of course A would be lower limit and B would be the upper limit, and that also depends on the direction of vector field. If the vectors they are going from A to B, then of course the lower limit has to be A and upper limit has to be B. Now in this case, as we studied in line integral of vector field, we discussed that the value of integral depends on the path joining these 2 points. We have already discussed this. But there are some other types of fields for which this line integral depends only on the points A and B and not on the path taken. There are such fields present. So that means the value of the line integral, okay, fine, again see, whenever vector is present and we have 2 points in the vector field and we will draw any curve between them, and if a line is drawn or a curve is drawn, we have to take line integral to get the solution. We have no other choice, because a curve or anything like this, like you can see this blue curve, or if in this figure this orange, green and this other blue color, they all represent curves, but still they are one dimensional. So we have to take line integral. But in certain fields, the line integral taken would only depend on the limits, the lower limit and upper limit, and it will not depend on the path taken. So it doesn't matter which path you take, the answer will only depend on these 2 points A and B. So the path C would be an independent factor. It would have no role on the value of this line integral. So such fields are called conservative fields. We have the definition here that the fields for which the line integral turns out to be dependent only on the endpoints A and B, but is independent of the path C connecting the points A and B, they are called conservative fields. So here you can see that if we say that a particular field, suppose vector A is a conservative field, then its value will only depend on A and B, and it will not depend on the path C. So whenever we write down this line integral along a path C, before this C had some importance because it was influencing the final result, the final value of integral. But for conservative fields, this C has no role. Conservative fields are independent of the nature of the path taken. To understand this, that what kind of fields are actually which are conservative. So let's consider that vector field A is basically this del phi. Now what is this del phi? It is gradient of a scalar function, because we represent the scalar function by phi. And of course we know that gradient of a scalar function is a vector quantity, because it's a vector, because scalar function is a scalar quantity, but this del operator, it's a vector. So when it operates on this scalar quantity, what we obtain is a vector quantity. So we can relate vector A to B equals to gradient of scalar function. So now you know that this del phi means gradient of scalar function. So if that's the case, then we can write down our this integral, line integral, to be equal to A to B A dot dr, which we already know what is it. Okay, because after all the points are A and B. And now if we substitute the value of A, which is del phi, we can write it at like this. And now this thing, this particular thing has a value. When we were discussing gradient of a scalar function mathematically, in that topic we discussed and we actually solved the value, and this value is equals to d phi. We have actually solved this, so you can check that video of mine. The topic is gradient of a scalar function. There we solved it and we actually came to conclusion that this particular relation is equals to d phi. Okay, so now here directly I am going to use that rule, that formula. Now you can see that this is simply d phi. Phi was a scalar function and d phi denotes a very small change in phi. Of course, it has to be a scalar quantity. Now you see, it simply depends on that scalar function because our vector field A was del of phi. So ultimately, some scalar field is present there and we are taking the gradient of the scalar field. So gradient tells us the rate of increase, it gives us the direction of maximum increase. So where there was maximum increase in phi, and phi is a scalar quantity, that direction of increase is vector A. So ultimately we are dealing with phi, and phi is a scalar function. So all we have is a scalar quantity. So this b phi is just a numerical change, numerical value, denoting only the change in phi. So if we'll take the integration of this, we would get this thing. And of course, we have to put the limits. And when we substitute the limits, what do we get? We get phi of b minus phi of a. This is our answer, because we know that phi is a scalar function which also depends on x, y and z. And a and b, they are just points in some space. So if these points change, the value of phi would change. But that's it. Now here it's clear that this value of integral, line integral, depends only on the points a and b and nothing else. All we have to do, no matter what's the path, is there any indication of path being involved? No, no path is involved here, because all we have to do is, we did include the path before, but not now. Like in the answer, it's somehow gone. All we have to do is just put the value of a and see what is the value of phi, and then again by putting b, what's the value of phi, and the difference would give us the answer. So here, this, whatever vector field a is this, it is depending on phi. So this means that if there is some vector field which looks like this, which looks like del phi, then of course its integral would be independent of the path. Let's see its definition. So one of the definitions says that if line integral a dot dr over the curve c, we will consider some path, is independent of the path. So whatever your path c is, this value of integral is not depending on that path. Then the vector field a is said to be conservative. And this condition is often satisfied by vector fields which look like this, del of phi. That means, fine, we will take line integral of some vector fields, but there are also types of vector fields. Some vector fields are fields made by vectors, but some vector fields are the fields obtained by taking gradient of scalar fields. Now you can see the difference. We know scalar function and vector function both have their own fields. Field of scalar function is called scalar field, field of vector function is called vector field. So when we have a vector function present, of course, we would be having vector field and the vector function a, and we would try to find the line integral. And in that particular case, the answer of the integral would depend on the path. But if you have a scalar field, but you are obtaining a vector by taking the gradient of scalar field, because we know if we take gradient of scalar field, we will obtain a vector. So the vector field that we have obtained is actually the gradient of scalar field, which is giving us a vector feeling. Now you know that, because gradient tells the direction of maximum increase. So if your quantity is scalar, no matter the quantity is scalar, but still the gradient would give you a vector feeling. So you would see a vector field. So if something like this is present, if scalars are involved, then the answer of your integral would be independent of the path. And such fields are called conservative fields. They just conserve themselves. Conservation means what? Just to keep themselves as it is. So they are not changed. Here you can see that no matter what path you take, answer is not changing. The value will not change. So this is what being conservative means. Okay, so this is one type of definition. Then we can have another definition like this. This definition also looks almost similar to the first one. It says that a vector field A is said to be conservative if it can be expressed as the gradient of some scalar field. So that means, to be a conservative field, we need scalar quantity. We need some scalar fields present. Because if we have scalar fields, definitely we would try to find gradient. Now you know we cannot find divergence of scalar quantity, we cannot find curl of scalar quantity, because those two terms are meaningless for scalars. For scalars, we only have gradient. So if some scalar fields are present, obviously we'll try to find the gradient, and that gradient would actually give us a vector. So if a vector is made up of a scalar field, then definitely it's going to be conservative. And we can understand this by taking, like, suppose we have this vector with us, and if we take curl on both sides, what do we get? It's del cross A. As you know, curl means when you take cross product with del operator, and here we would get this del cross del phi. And as we did in the previous video, that curl of gradient of scalar field is always 0, and this right hand side actually represents curl of gradient. See, we know that del phi is gradient of scalar field, and then we are taking curl of it. So it's curl of gradient, and it is 0. So this implies del cross A is equals to 0. And also, see, this is cross product, del and del. So means if same quantity, if same vector is having cross product with itself, it's always 0. Okay. We have done this when we were just studying the dot products and cross products. There we had this rule that if same quantity is having cross product with itself, then it turns out to be 0. So in that case also, if we have del cross del, it is going to be 0 anyhow. But here we are using the quantity because there is some other rule which is even more important, which states that curl of gradient of scalar field is 0. So that's why we have used that formula here. So now what does this del cross A equals to 0 means? We know that if curl of any vector field is 0, then that means that that particular vector field is irrotational. So this implies your A is irrotational. That means the vector A is not rotating at all. So this also gives us some indication that whenever we have any vector field which is not rotating, then there are chances that it can be a conservative field. All these things, they are just giving us some indications. So whenever we see any particular field present, we try to find all the things attached with it, that we try to see that whether it's rotating or not, and if it's not rotating, then we can state, I mean, I'm not sure, we cannot say with surety, but there is indication that there may be some conservative field, because now just by calculation we have derived that a conservative field is irrotational, and that is for sure. If it is a conservative field, it will not rotate. So whenever we detect any fields present at any point, we try to see their behavior, and if we see that they are not rotating, then we can assume that it could be a conservative field. But to detect whether it's a conservative field, we have to do some more calculations. Okay, so this is how we use all these mathematics together to gather the knowledge. Now let's consider the third definition, which is a bit different. It states that a vector field A for which line integral around a closed curve vanishes is called a conservative field. Till now we were just discussing curves, but here it states closed curve. Okay, so this is something unique. Till now we were just dealing with one-sided curves, non-ending curves, but here it states something about closed curves, so something which is closing. So if the line integral around a closed curve vanishes, that means the value comes out to be 0, then that particular field is also called conservative field. In that particular case also, it means that the vector field is conservative. Also, we can say that if the curl of some vector field is 0, then that field is conservative, as we just proved. In conservative fields, they are also known as irrotational or lamellar vectors. Okay, these are just other names. Now, this third definition stated something about closed curve. So let's discuss. So here again, now we know that conservative field depends only on initial and final points. So this A and B are our initial and final points. Okay, but still here we are not saying that we already know conservative field. We would prove that the value of integral would come out to be 0. And if that happens, then that means this vector field A is conservative. So you can see this vector field A here present, and we have taken 2 points A and B in this field, and we have drawn two curves, one going from A to B and another going from B to A. And now you know that in case of vectors, direction really matters. So if you are going from A to B, the value of integral would be different, and if you are going from B to A, then the value of integral would be having opposite sign. Though the value obtained would be same, but it will come with a negative sign. It would be negative of what obtained from A to B, because direction is changing and we are dealing with vectors. So direction really matters, and the value of integral would be opposite in sign, though same in magnitude. Now let's see. And also, whenever we say that we are taking line integral of vector A over a closed curve, now we actually made two curves, this going from A to B is C1 and the other going from B to A is C2. But now you see they are just joining together, so this makes a closed curve, and this is a closed region between these two curves. Whenever we take line integral of vector field A over a closed curve, then that is called circulation of A. Circulation. It's just going around in this circle. Though it's not a circle, it can be any figure, but it's a closed path. So we call it circulation. And there is a way to denote it also. There's some different way of notation. Let's see. This is represented by A dot dr integral over the closed curve C, and we make this round. Normally, when we just talk about simple curves which are not a closed curve, we mention A dot dr and we simply write down the curve C, because that in that particular case the curve is not closed. Okay, it's simply joining. So it's just a line, we call it. So in that case, we simply represent the integral and we just mention that whatever curve, whatever path, if there are many paths involved, like this, so this is C, this is C1, this is C2. So whatever path we are considering, we just mention that path as name. But if we are talking of something which is closed, so here we are saying that it's a closed curve C basically. So let me denote it by that. This is a closed curve C. Okay. We made two paths, C1, C2. Okay, so C1 and C2, they are different, but they are joined now, and this entire path becomes a closed curve C. So in that case, we would mention the name, and we would also make this circle over this integral, which shows that we are talking of a closed curve. We are talking of a closed path. So one thing is sure, that if we just find A to B along C1, if we consider only path C1, then its value would be minus of that along C2. Why? Because directions are changed. So this thing is fixed. Now let's find what is A dot dr. As we discussed before, that A dot dr and A here is gradient of scalar field, because this all can happen only if vector field A is gradient of some scalar field. So del phi we have taken, and it's having dot product with dr, and now we know that del phi dot dr is always equal to d phi. So we obtain d phi, and then if we just solve it, we would get phi b minus phi a. This is what we obtained before also here. Okay. this is the same result. And now what would be the answer for this A dot dr along curve C2? Now it's going from B to A and curve is C2. In that case, again, we would be having B to A along curve C2 del phi dot dr, which would give us d phi. And here we have this from B to A, because it is curve C2 represent the vector going from B to A. So again, this would be phi, and we have to substitute the limits, and that would give us phi A minus phi B, because it is always upper limit minus lower limit. And now we want to find what is the line integral over the closed curve. We have made this closed curve by joining two curves, two non-closed curves or two open curves. C1 was open curve, C2 was open curve. They were joined to form a closed curve C. We found what is line integral along the open curve C1. We have found what is the line integral along the curve open curve C2. And now we want to find what will be the line integral along the closed curve C. So in order to find that, what we need to do is simply add up. Simply add the line integrals of both the curves. So this is the thing. Here you can see that I have represented this closed curve. See, the only difference, the way of demarcating a curve from being closed or open is that for closed curve, we make this round circle over the integral. So here this C means the closed curve, this entire closed curve C. Okay, that is made up of the curves C1 plus C2. So now we have to just add the results of both the integral. So that would be phi B minus phi A plus phi A minus phi B, which is the result from curve C2. And now you can see we can just cancel these and we obtain 0. So if line integral along a closed curve comes out to be 0, this is what it means, that a vector field for which line integral along closed curve vanishes. This is the meaning of vanishing. Okay, this is what vanishing means. This highlighted portion actually tells you that line integral along a closed curve vanishes. Vanishes means the value comes out to be 0. And yes, we have obtained a 0 value. This is our 0. And we were actually finding A dot dr along the closed curve C. So this is another way to detect whether a particular field is conservative or not. If we are having a closed curve and we just find the integral, the line integral over it, the best way is always to break it up into different curves. So whatever curves make that closed curve, you have to take the line integral along all those open curves which actually join to form a closed curve. And if by doing so the value comes out to be 0, then it is clear that the vector field present is a conservative one. And one more thing which is important is that that particular vector field should not be a field due to a vector. In fact, it should be a vector field obtained by taking gradient of a scalar field. So this is how scalar field is so much important for us. So line integral of conservative field over a closed wire is 0. Or we say that circulation of conservative field is always 0. So this statement is also important, that line integral of conservative field over a closed wire. And see, closed wire, that means that we are considering line integral. We are not considering any surface. This thing that we draw, whenever we draw something like this, of course it is enclosing some surface, but here if it encloses, then we would show it with some highlighted region that we are considering a surface. But if we are not doing so, in that case it simply means that we are talking only about the path. And that's the reason that we are saying here that it is just a closed wire. It is just a closed loop, a closed path, just a one-dimensional, just to give that one-dimensional feeling, so that we can justify that we are taking line integral, and that is the only possible way here. And also, since we said that line integral of vector A over closed curve is called circulation, so again, circulation of conservative field is always 0, which means that its line integral over the closed surface, not the closed surface, over the closed path would be 0. This is the thing, that all the words that we choose, they should be really important, because if I say closed surface, then that means I'm talking of surface integrals. I'm enclosing some area, but no, here we are just talking of line integral, and that's why the words that we choose is really important. So for line integral, we can only have path, track, loop, wire. We can use these words. So this was all about conservative field, and in the next video we'll discuss surface integral. So as I told that we have three types of integrals that we deal. It's line integral, surface integral, and volume integral. So the next video is for surface integral, and yes, we'll discuss volume integral as well. That's all for today. Thank you.